All right, so we only have a few more things left to wrap up for this particular video. The first one is going to be molecular polarity, and the last thing we're going to look at is our covalent bonding nomenclature. So I want to take the concepts that we last looked at and use bond polarity to actually solve for molecular polarity. And it's important because it determines the relative strength of forces in between different molecules within the same material. So like I said, we'll discuss that a little bit later on. But for now, let's discuss the concept of molecular polarity. Polar molecules show asymmetrical electrical charge, whereas nonpolar molecules show symmetrical electrical charge, meaning that the distribution of electrons is even. It can be a bit tricky to determine this. There are a few tips and tricks to going through and determining this, but how we go through and we follow this is very similar to what we've done previously. First step is to draw the correct Lewis structure. Second, determine the correct geometry and draw accordingly. 3, draw your dipole arrows for each bond in the molecule. So that's the additional step here, is look at the dipole arrows that exist within the molecule. And then the next step is to find the situation that best fits the molecule. Nonpolar molecules will have either all nonpolar bonds, so we wouldn't draw any dipole arrows, or polar bonds that cancel one another. Polar molecules are going to have unbalanced polar bonds or lone pairs on your central atom. Now I know that that is going to be different for each class, because this class is a fairly simplistic representation of molecular geometry, polarity, and intermolecular forces. Lone pair on your central atom are going to be an indication of polarity. So a couple different ways we can go through and do this. So a couple of examples here. I've put 2 different molecules here for us to determine the molecular polarity for. The first one here is CO2. And notice I draw the dipole arrows that are pointing away from carbon. That is because oxygen has a greater electronegativity than carbon does, and there are 2 carbon-oxygen bonds that are here. Okay, so notice that we have 2 dipole arrows. They are pointing directly opposite of one another. So these would cancel one another. Another way to look at this, and this has been quite successful for some of my students, is to think of these as forces that act upon the molecule. So in that carbon dioxide molecule, you have a force that's pulling to the left, and you have a force that's pulling to the right, and they're pulling exactly opposite of one another. Well, that molecule is not going to move. It's going to be completely stationary, and if that molecule remains stationary, you can consider it to be a non-polar molecule. Consider the H2O that's listed down there below as well. You have 2 dipole arrows, both pointing towards oxygen, but notice that they're not exactly opposite of one another. They cancel each other left to right, but both of them are pointing upwards, so the molecule would still be considered polar because the dipole arrows don't 100% cancel each other. If you had one pointing up and one pointing slightly down, they would cancel each other, but both are pointing up. This means that their dipole arrows don't cancel, so it is considered a polar molecule. This is one of those things that's just going to take a lot of practice in order to get really, really good at. Look at HCN, for example. We've drawn 2 dipole arrows here, one between hydrogen and carbon and one between carbon and nitrogen. The carbon-nitrogen dipole arrow points to the right, and the hydrogen-carbon dipole arrow points to the right as well. Now, if you were to follow my rules, you actually wouldn't draw a dipole arrow with hydrogen and carbon because we consider that a non-polar bond. But regardless, you have 2 dipole arrows that point to the right. Neither of them cancel each other out, so this molecule is also considered polar. So again, it really focuses in on following the rules, determining the geometry, and figuring out, do my dipole arrows cancel or do they not cancel? There's other ways to determine molecular polarity. I think I have a few hints on the next slide, but for right now, let's go through and practice with this together. Let's determine the Lewis structure, geometry, and polarity for the following molecules. Take a few moments, we'll do this together, and then we'll come back and wrap things up because I've got one more thing I need to discuss. All right, so I've zoomed in a little bit for each of these because I want to draw these Lewis dot structures out and kind of go underneath to figure out the rest of this. So bear with me as I go through and relatively quickly draw out these Lewis structures. But again, kind of the benefit of knowing what you're doing makes this a lot easier. And then what we'll do is we will go through and, not do that. There we go. One of these days I'll learn how to work with my iPad, but for the time being, just bear with me as you're going to have to suffer through the immense pain of watching me try to get all this figured out. Oh goodness, there's plenty more left. Okay. PF3, I can do that. SCl2, and CH3Cl. Just making sure I have enough room here. Okay. So now let's go back and determine the geometries for each of these. Okay. So for the first one here, we have a steric number of 4 and 2 lone pair. So that is going to be bent. The next one here, we have a steric number of 2 and no lone pair. So that is linear. For the next one over, we have a steric number of 4, again, atoms plus lone pair. We have a single lone pair, so that is going to be trigonal pyramidal. Next one over, steric number of 4. I know I'm working through it pretty quickly, but again, you practicing is what's going to make this better. So keep working on it, keep practicing, keep getting better. And then the last one here, we have a steric number of 4. No lone pair, so that is tetrahedral. Okay, so now the next thing I need to do is I'm going to go through and I'm going to draw some dipole arrows on these. And our job here is to determine, do those dipole arrows cancel? Do they not cancel? And then is this molecule polar or non-polar? Oh, I didn't even do this first one here. Silly, what a silly goose I am. Steric number of 4, no lone pair, is tetrahedral. Okay. So now we draw our dipole arrows. First thing I notice here is that each bond is going to be needing a dipole arrow if it is a polar covalent bond. If it's non-polar covalent, we're not going to draw it out. So the first one here is CH4. Remember that carbon and hydrogen are considered non-polar bonds. So this has all non-polar bonds. There's no dipole arrows, so this means that this entire molecule is non-polar. Next one here. Our dipole arrows, remember they point towards the atom of higher electronegativity, so we're going to point these both up towards the oxygen. Okay, and then again, we have to ask ourselves, do these dipole arrows cancel? And the answer is no. And again, you can also utilize the concept of we have lone pair on our central atom. So this molecule is polar. CO2. Dipole arrows are going to point outwards towards the oxygen due to oxygen having a higher electronegativity than that of carbon. Again, ask yourself, do these dipole arrows cancel? Yes, they do. So this is a non-polar molecule. So even though it has polar bonds, it is a non-polar molecule because those dipole arrows cancel each other out. PF3. Our dipole arrows are going to point towards the atom in the bond with higher electronegativity. So between each phosphorus and fluorine, fluorine will have the higher electronegativity, so arrows will point outwards. Notice that all 3 of those dipole arrows do not cancel. Okay, the one up here at the top, there's nothing in the bottom that goes through and cancels with that. In addition, we also have that single lone pair on your central atom is a polar molecule. SCl2. Same thing here. We're going to point our bonds or our arrows to the atoms in the bond with higher electronegativity. Those will not cancel. So I even rewrite these in the correct geometry to get a better idea of whether they'll cancel or not. We also have lone pair on our central atom, so this is polar. The reason why I draw these this way, and something you may want to do as well, is that when you go through and draw these out, you may want to go through and redraw them. And the reason I do that, let me show you why, is because if you were to draw this, let's say you were to draw this as if you thought it might be linear, and you were to go through and draw your dipole arrows just like what we just discussed, you might think that because you think this is linear, those arrows would cancel each other out. And we know that that is not the case. Because this is bent, the molecule's shape looks a little bit different than what it would if it were linear. So you need to take that into consideration when you go through and draw these out, is that if you didn't draw it in the appropriate shape, you may want to redraw it because that's going to help you determine the polarity of the molecule itself. Last one here is CH3Cl. Remember that carbon and hydrogen bonds are considered nonpolar. We have a carbon-chlorine bond here. The dipole arrow points to the right. There's nothing that's counteracting it. There's nothing that's canceling it out. So this molecule is also polar. So it is tricky, but practice is going to make this good. So draw those Lewis dot structures correctly, determine the geometries, rewrite the structure in terms of the correct geometry if you need to, and then determine the polarity based on the rules that we've gone through and previously discussed. Okay, let's move on. I wanted to provide just a couple of other hints into terms of determining the molecular polarity, because sometimes all of these steps can be a little bit difficult, and I like to provide shortcuts. The shortcuts are going to differ depending upon the professor and depending upon the class, but I found that for the most part, these shortcuts tend to make life a whole lot easier for individuals. So some polarity hints. Any molecule completely surrounded by the same atom is a nonpolar molecule, provided that there are no lone pair on your central atom. So CH4, for example, CCl4. All of these have the same atoms surrounding the central atom and have no lone pairs on that central atom. So those will be nonpolar molecules always. Any molecule with a lone pair on your central atom is polar. Again, different classes will differ than this. If you have expanded octets, sometimes that rule does not necessarily apply. So you can't always utilize that rule, but for me and for my class, you absolutely can. Any molecule with different atoms attached to the central atom is considered polar. So I used the previous example of CH3Cl. The carbon atom in the central atom had 3 hydrogens attached and 1 chlorine. Those are all different, so the molecule in and of itself will be polar. So these tips and tricks are actually quite helpful because it prevents you from having to do a ton of extra work to figure out the polarity of the molecule. And again, like I said, these rules will differ depending upon who your professor is and how the class runs.